Okay. In the last video, we completed the single slider crank mechanism inversions. Now, we are going to discuss in this video some of the problems. One or two problems we'll discuss in this Whitworth kick return mechanism and the crank and slotted lever mechanism. Then we'll move to the double slider crank mechanism and inversions of double slider crank mechanism. That will complete this first unit with this video. Now, we are going to start one problem. In a crank and slotted lever kick return motion mechanism, the distance between the fixed centers is 240 mm and the length of the driving crank is 120 mm. Find the inclination of the slotted bar with the vertical in the extreme position and the time ratio of cutting stroke to the return stroke. If the length of the slotted bar is 450 mm, find the length of the stroke if the line of the stroke passes through the extreme positions of the free end of the lever. So this is the given problem. Now given data I are writing. So length of the AC is equal to 240 mm. CB1 is or CB is the crank length 120 mm. So AP1 or slotted lever length is 450 mm. So now inclination of the slotted bar with the vertical, we have to find out. So let angle CAB1 is the inclination of the slotted bar with the vertical. The extreme positions of the crank are shown in figure. Okay, this is the extreme shown in figure. Now this angle values you have to find out. Okay, 90 minus alpha by 2 and 90 degrees you are observed from the figure. So this is the figure you are observing. Now we have to sin angle CAB1 is the sin 90 minus alpha by 2, that equal to B1C by AC, that is 120 by 240. So now from this we can try calculate as angle CAB1 is 90 minus alpha by 2 is the sin inverse of 0.5, that is 30 degrees. Okay, this is the value. So this angle value is 30 degrees. Next one is alpha value you can calculate. Okay, from this 90 plus 90 minus 30 is alpha by 2, or alpha is 120 degrees. So remaining time of cutting stroke to time of return stroke ratio is 360 minus alpha by alpha, or 360 minus 120 by 120, that is 2 ratio. So now length of the stroke you can calculate from this. R1 R2 is equal to P1 P2 is equal to 2 P1 Q, that is 2 AP1 sin 90 minus alpha by 2, that is, so 2 into 450 into sin of 90 minus 60, so that is of 900 into 0.5. Okay, the 450 mm is the length of the stroke. So this is the way you are calculating. Next problem. So in Whitworth kick return motion mechanism, as shown in figure, the distance between the fixed centers is 50 mm and the length of the driving crank is 75 mm and the length of the slotted lever is 150 mm and the length of the connecting rod is 135 mm. Find the ratio of the time of cutting stroke to the time of return stroke and also the effective stroke. So this is the given problem. From this we are drawing the figure like this. So this is the crank and Whitworth kick return motion mechanism figure. So we can calculate time of cutting to time of return stroke. I have to calculate. For this given figure, CD is equal to 50 mm, CA is equal to 75 mm, PA is equal to 150 mm and PR is equal to 135 mm from the data. Now the extreme positions of the driving crank are shown in figure from the geometry. So like this. Okay, from this we are calculating beta by 2. So cos beta by 2 is CD by 8 CA2 from the figure. So that is 50 by 75, that is 0.6767, or beta by 2 is 48.2 degrees, or beta is 96.4 degrees. We know that time of cutting stroke by time of return stroke is 360 minus beta by beta, that is 360 minus 96.4 by 96.4 is, that is 2.735. So this is the way of calculating. Next one is length of effective stroke is R1 R2 value, that is nothing but R1 R2 is equal to 2 times of P1 R. This is the case. So we can calculate from the diagram length of effective stroke is R1 R2 is 87.5 mm. The next one is double slider crank chain. So kinematic chain which consists of 2 turning pairs and 2 sliding pairs, then it is called as double slider crank chain. Okay, now link 2 and link 1 form one turning pair, and link 2 and link 3 forms the second turning pair, The link 3 and 4 form the one sliding pair, and link 1 and 4 form the second sliding pair. That is two sliding pairs and two turning pairs. Therefore, it is called as double slider crank mechanism or double slider crank chain. Now we have to discuss about inversions of double slider crank chain. First one, okay, different inversions are there. First one is the elliptical trammel. Elliptical trammels, so it is an instrument used for drawing ellipse. So to draw the ellipse, this can be used, elliptical trammel. This is the inversion is obtained by fixing the slotted plate. Okay, slotted plate is fixed. Now the fixed plate or link 4 has two straight grooves cut in it at right angles to each other. The link 1 and 3 are known as sliders and forming sliding pairs with link 4. The link AB is a bar which forms turning pair with link 1 and 3. When the link 1 and 3 slides along their respective grooves, any point on the link 2, such as P, traces out an ellipse on the surface of link 4. Okay, like this. Now electrical consideration will show that AP and BP are the semi-major axis and minor axis, semi-minor axis of the ellipse respectively. This can be proved as follows. So this is the case we are observing. Now the P is the point, tracing point is ellipse. Okay, any point P is moving and that ellipse shape is moving. So now AP is the major axis and BP is the minor axis will be the case. So from this way it will be moving. Two sliders A and B in a slotted lever at right angles are connected to the bar link 2. So now this slotted bar is fixed. Now two links A and B are the sliding with the link 4 fixed link. Now bar is oscillating. Okay, like this it is moving. Now in this case we are observing the P point position is at a distance of from the O, horizontal distance x, vertical distance is y. So this relation you can find out. Okay, elliptical trammel. And now at OX and OY is the horizontal and vertical axis. Let the link BA is inclined at an angle with theta with the horizontal. Now the coordinates of the point P on the link BA will be the XY. Now x equal to PQ, that equal to AP cos theta, y equal to PR, that equal to BP sin theta. So that is x by AP is cos theta, y by BP is sin theta. So by taking squaring and adding that values, x square by AP square plus y square by BP square equal to cos square theta plus sin square theta, that is 1. So therefore this is the equation for an ellipse. Hence the path traced by point P is an ellipse whose semi-major axis is AP and semi-minor axis is BP. So if P is the midpoint of link BA and then AP is equal to BP, that is the above equation can be written as this will become this equation will become circle. Okay, circle whose radius is AP. Hence if P is the midpoint of link BA, it will trace a circle. So P is the midpoint of AP, then it will be a circle. Next one is Scotch yoke mechanism. Second one is the Scotch yoke mechanism. So now, in this case, converting rotary motion into reciprocating motion. So the inversions is obtained by fixing either the link 1 or link 3. So now the link 1 is fixed in this mechanism and the link 2 rotates about B as center. The link 4 reciprocates. The fixed link 1 guides the frame. So now we can observe this is the figure, Scotch yoke mechanism figure. So link 4 is the fixed frame and link 2 crank and slider is the case. Now this will be link 1 is the starter. Now this is more crank rotates about fixed point B, then A is slider reciprocates. Okay, slider sliding along the slotted bar, then piston reciprocates another link 4. Like this it will be moving. Okay, two sliding mechanisms and two sliders and two turning pairs are there. Now next one is the Oldham's coupling of this last inversion of the double slider crank mechanism. So in this case figure here you can observe two flanges are there. So then flange 1, first flange is the link 1, next flange is the link 3, intermediate piece is the link 4 and the driving shaft is the driven shaft which are connected to this flanges. Okay, now supporting frame is the link 2. So now these are the cases, 4 links are there. So that is driving shaft with flange 1 and driven shaft with flange link 3. So fixed frame is the link 2 and intermediate piece is the link 4. So now the intermediate piece is placed like this. So 2 grooves are provided on this flanges, so that in that grooves, so the intermediate piece will be fixed in a link opposite direction perpendicular to this T1 and T2, so like this. So they are moving. So an Oldham's coupling is used for connecting two parallel shafts whose axes are parallel are at a small distance apart. Okay, two shafts are connected by means of this coupling rod or Oldham's coupling. So the shafts are coupled in such a way that if one shaft rotates, the other shaft also rotates at the same speed. Okay, this inversion is obtained by fixing the link 2 as shown in figure, that is fixed link or frame. Now the shafts to be connected have two flanges rigidly fastened at their ends by forging. Now the link 1 and 3 form turning pair with link 2. These flanges have diametrical slots cut in the inner faces. Now the intermediate face, which is a circular disc, have two tongues, now T1 and T2 on each face at right angle to each other. Now the tongues on the link 4 closely fit into the slots in the two flanges. Now the link 4 can slide or reciprocates in the slots in the flanges. When the driving shaft A is rotated, the flange C causes the intermediate piece to rotate at the same angle through which the flange has rotated, and further rotates the flange D at the same angle, and thus the shaft B rotates. Hence link 1, 3 and 4 have the same angular velocity at every instant. Literally now there is a sliding motion between the link 4 and each of the other link 1 and 3. So if the distance between the axis of the shaft is constant, the center of intermediate piece will be describe a circle of radius equal to the distance between the axis of the two shafts. Therefore the maximum sliding speed of each tongue along each slot is equal to the peripheral velocity of the center of the disc along its circular path. Now omega is the angular velocity of each shaft, then r is the distance between the axes, then maximum sliding speed of each tongue is V is equal to r omega. So this completes the double slider crank mechanism inversions. Now this completes the first unit of this total 6 videos. So thank you. Now in the next video we will start the second unit, that is straight line mechanisms. Okay, thank you.